Next, we'll look at the reduction operators. In Verilog, the reduction operators are used to condense all the bits in a vector into a single bit. Here are 4 of the reduction operators. The first thing you'll notice is that they use the same operator that we've seen previously for the AND, OR, exclusive OR, and exclusive NOR. This may appear strange as we've already used these for the bitwise operators. The reduction operators are unary operators, meaning they operate on one operand. We could have &a, which represents the reduction AND operator, and this operates on a single operand. So note the difference between A &B and &a. In this case, we have the reduction AND operator, and in this case we've got the bitwise AND operator. So we have the reduction AND, reduction OR, reduction exclusive OR or reduction XOR, and the reduction exclusive NOR or the reduction XNOR. In addition, there are 2 further reduction operators, the reduction NAND and the reduction NOR. The reduction NAND operator is given here, and the reduction NOR operator is given here. The bitwise operators are listed on these 3 rows. So we've got the bitwise AND, the bitwise exclusive OR, the bitwise exclusive NOR, and the bitwise OR. And these are all binary operators, meaning they operate on 2 operands. The bitwise reduction OR operators are listed at the top of the table, indicating that they have the highest precedence. There are some additional unary operators also at the top of the table, but let's just focus on the bitwise reduction operators. And you can see the 6 reduction operators. We have the reduction AND, the reduction NAND, the reduction OR, the reduction NOR, the reduction exclusive OR, and the reduction exclusive NOR. The result of the reduction operator is always an unsigned value and of size 1, so it's just a single bit result. As noted, the reduction operators are all unary operators, and it's a self-determined operator. So let's see exactly what these operators do. In our example, we have the reduction OR operator. If we take the following value for A, 0, 1, 1, 0, 1, what the reduction operator does with this value is it ORs all the bits together to produce a single result. So it's equivalent to the following. In our example, having an OR gate with 5 inputs with 5 single bits to represent our 5 bits, 0, 1, 1, 0, 1. And in this case, the result is 1. The output from the operator in this example is 1. So it proves a useful way to take a group of bits and, in our example, OR all those bits together to obtain a single bit result. Another example, 0, 1, X. We again can think of it as a 3 input OR gate with the bits 0, 1 and X. And we know for an OR gate, if any one of the inputs is a 1, the output is a 1. So again, we have a 1 here. If, for example, this was a 0, our output now is an unknown X. The previous tables we detailed when using the 4-bit value set apply for the reduction operators also. For example, some of those tables are shown here. Let's take one more example, this time using the reduction AND operator. If we've got ampersand A in our code, let's say with 3 bits, 0, 1, 1. In this case, the 3 bits are ANDed together, and you can see that that's going to yield the value 0. If we've got X, 1, 1, think of it as a 3-input AND gate. The output is unknown because it depends on whether x is 1 or 0. So in that case, the output is x. If our input value is 1, 1, 1, we now have an output 1. The possible outputs for the reduction operators are the three values 0, 1, and x. The reduction OR operator is an important one to be aware of, as it is implicitly used by certain statements in the Verilog language that we will encounter later. Our next group of operators are the shift operators, and we'll start with the logical shift left and the logical shift right. So the logical shift left is given by this operator and the logical shift right by this one. Just taking the shift left, you can see what happens is that zeros are inserted from the left hand side into an operand. So it's a shift operation moving the bits from right to left, inserting zeros in from the left side. As an example, let's take the following 10 bits and let's shift the bits to the left using a logical left shift by 4 places. So what happens when we perform a 1-bit shift is that the 10 bits are shifted to the left and we lose the most significant bit as there's nowhere for it to go. So we've 9 bits and we now have a space for the least significant bit. So a 0 is shifted into that space. That's a single bit shift. Let's do it again, shifting the 10 bits on this row, shifting the 10 bits here to the left by 1 bit, and we have the following. We lose this bit because there's nowhere for it to go, and we have a vacancy here which we fill with a 0. So at this point we've performed a 2-bit shift. Let's do it again. Let's do another single bit shift, and this is what we have, one more, leaving us with this 10-bit value. We've performed a 4-bit logical shift left operation. And with our 4-bit shift, we've shifted these 6 bits to the upper 6 bits, and we've inserted 4 zeros in the vacant positions. And as a result of our logical shift left operation, we lose the 4 most significant bits of our original value. Let's take an example. Here we have A, and B is a 3-bit vector of type reg. Giving A a value, 10 bits, we'll specify the value in binary, and we give B the value 4. So what we have is the following: A 10-bit value, and B is a 3-bit value representing the value 4. Let's just take the expression A logical shift left B. The basic idea with our logical shift left is that the second operand specifies the number of shifts to the left. So in this case our value is 4. So we take our 10-bit value and insert zeros from the left side. Now you'll note I haven't specified what the output size is. In this example, our output will be a 10-bit value. So we take our first operand, shift it left 4 places, and insert zeros. So let's do that. We insert our 4 zeros. 1, 2, 3, 4. This is our LSB, and this is the LSB of our operand. So we've inserted 4 zeros, and then we have 1, 0, 0, 0, 1, 0. So you can see the operation. We're inserting zeros and shifting our operand to the left. We lose 4 upper bits of our original value. That's the basic idea with logical shift left operator. Note that our original A is not modified here. We just use the value in A to produce a result. We now need to talk about whether this is a context or self-determined operator. And it turns out that it's a bit of both. It's not fully context and it's not fully self-determined. And we can illustrate that in this way. So it's part context and part self-determined. The output size is context determined, and it depends on the first operand and other parts of the expression. So for example, if we have sum plus A logical left shift B, what happens here is that the output will depend on A and sum. So the output is context determined. And if sum was a 12-bit value, our output would be 12 bits. And we'd need to extend our 10-bit to a 12-bit value. And this is the normal approach for context determined operators. The actual type of extension will depend on whether the first operand and sum is signed. So this will be a signed extension if A and sum are both signed. Otherwise it's unsigned. So the way to think about this operator is that the second operand does not influence the output size or how the extension is done for the first operand. The second operand is always interpreted as an unsigned value. So even if B is signed, the value that's used is interpreted as unsigned. That makes sense because the shift value is interpreted as a non-negative value. So to summarize then, this is part context, part self-determined. The output size depends on the context, and that includes the first operand for the shift operation and other parts of the expression. The type of extension follows the normal rules for context determined operators, and the output sign is determined by the first operand, A here, and the signedness of the remaining expression. There are two additional shift operators, the arithmetic shift left and the arithmetic shift right. It turns out that the arithmetic shift left operator is identical to the logical shift left, so we can ignore that. It has no practical purpose. And that leaves us with the arithmetic shift right. So we have a typo, there should be no R. So the only difference between these two operators is that when we're shifting right with the logical shift right, we insert zeros as we shift the value to the right. And for the arithmetic shift right, we replicate the MSB as we shift right. So just to give you a quick example, if you've got A arithmetic shift right 4, and let's say A is a 6-bit value with the following 6 bits, our 6-bit value is shifted to the right 4 places, and because the most significant bit is a 1, we replicate the 1 4 times. Shifting the 6-bit value 4 places to the right will mean that we lose the 4 bottom bits. The first operand, A, has the value 1 0 1 0 0 1. And if we just draw a line here, shifting it 1 place to the right, we get 1 0 1 0 0 1. And you can see that the MSB is fed in. So this is our MSB. So that's fed into the empty position. So that's one shift. So we only have a 6-bit result. So we lose that value. Let's shift it a second time. So taking our 6-bit value and shifting it to the right, 1-bit position, we have 1 1 0 1 0 0. So again, we lose this and insert our MSB into the empty position. So that's 2 shifts, and performing 2 more shifts will give us the following 6-bit value: 1 1 1 1 1 0. So this is our result after shifting our original value 4 places to the right, performing an arithmetic shift right. Shifting 1 bit to the right is equivalent to dividing by 2, and shifting to the left is equivalent to multiplying by 2. The purpose of the arithmetic right shift is to ensure that we preserve the correct sign of the number as we shift to the right.